Right. We're going to solve the problem. Sort vowels in a string. All right. So let's jump straight into the problem definition. Right. So the problem is that we are given a zero index string s. I need s to get a new string t such that consonants remain in the original place, or formerly within index. So psi is a consonant. A equal to psi. Vowels must be sorted in non-decreasing order of their ASCII values. So this right. So return the resulting string. So keep the consonants in their same places, but sort vowels in ascending order and descending order. Vowels are basically A, I, O, U, either uppercase or lowercase. And consonants are everything else, either uppercase or lowercase. So basically, the string itself can have any uppercase or lowercase letters. That's all. It doesn't have any other non-alphabetical letter characters. Okay. So we are also given like maximum length of the string can be up to 100,000, 10 power 5. So we cannot simply do a quadratic kind of a solution. So we need to do linear or like max and log n kind of a solution. Okay. So that's what maximum length is telling us we cannot do it for quadratic. Right? So what can we do here? I think the um, simplest thing that we can do is like uh, we can keep an array, we can create an array the same letter as, and for each position, for each index I in s, if it's a consonant, we just place the same letter in our array. But if it's a vowel and we add it to a second list, finally we can sort the vowel array, vowel list, and fill in our main first array in the sorted order of the vowels. That gives us an order n memory. And for sorting vowels, at max it's going to take order n log n. So total order n log n time complexity with order n memory. Another easy solution is that instead of just sorting all the vowels, because there are only five vowels in total, or max 10 if you consider uh, lowercase and uppercase, you can just keep count of each of the vowels that we see in this input string, and finally we just take them in the increasing ASCII order, right? So one thing that we need to get is like capital letters or uppercase letters will have lower ASCII letters, lowercase letters, right? So so yeah, I'm going to keep an array called vowel counts, and it's simple. I'm using a default thing. So basically, whenever we say a new element for the first time, its value is going to be 0. Uh, and this vowel counts keeps the count of the vowels that we see so far in the array. Uh, right. I'm also keeping result list, or let's call it plist. String opens. So what we are doing here is like if we see the model, we simply update the vowel count and structure. Otherwise, in the final output list, we simply simply copying the character in its own. That's right. So now finally, all we need to consider is like so basically I am keeping this vowels array, which is a list of the vowels, such that they are already sorted in the ASCII order. Right? So now what we simply do is we can also uh, blank. So basically look for the next hole. So when we see a novel, uh, we are putting a hole in the T list, right? So, so make sure. Uh, so find the next hole. Yeah, so far so good. Let's subtract. Yeah, I think it's a decent enough kind of a runtime. Yeah, I think the it runs decent time. You can see that. So let's analyze this time and space complexity of this problem. So in terms of space, what we are doing is like uh, we are creating a list of size n, where n is the length of string, input string, right? So the space complexity is O(n), and also we are also maintaining a dictionary, basically counter of all the vowel spacing. But that counter will only have at max 10 elements. So that's O1 memory. And so total memory space is order n, space complexity. Right? In terms of time complexity, You can assume that dictionary operations are order 1. Anyway, there are only 10 elements in the dictionary, so order 1. Worst case, I would say. And iterating to the input string is order n. So here it's order n time complexity. And here, what we are doing is like for each vowel we encounter in the input string, and basically for how many number of times that it is repeated. That's what this two for loops mean. If we didn't see the vowel in the entire input array, then this vowel counts of that vowel is going to be 0. But if we see it say 5 times, then it's going to be 5. So basically, for each of the 10 vowels, and because they are already sorted in alphabetical order, what we're doing is like we start with an index I equal to 0, and we fill the current vowel in the next hole that we found. We iterate and we advance the index I after finding the next hole. Because the number of holes is basically the same as the total number of vowels in the input string. Of course, these things are going to match exactly. The difference being that just the vowels themselves are going to be in the sorted order or in the alphabetical, the ASCII order, and consonants are going to be the same place as they were before. So that's the analysis. Total complexity is going to be order n. Space complexity is also going to be order n. I think we can simply simplify it. We can simplify the code by not using a dictionary or counter. Simply use a list or an array basically, and simply append vowels to those lists, whatever we see in over. And finally, we sort the vowel list. So the time complexity is going to be order n log n for that, and space complexity will remain order n. But what's the advantage for that approach is like it simplifies the code a bit. You don't need to like you know don't need to do any of this. You could, after sorting, you can simply iterate through the sorted vowel. You don't have to do a double for loop. Yep, that completes the problem for today.